In this question, we will try to identify the correct peak wavelength and the temperature graph. So we will deep dive in this question and I will tell you all the background information that is required to solve this question. So in this question, we are talking about the black body, right? Although it can be applied for any object which is receiving the heat and then radiating, but specifically black body. Why? Because it is a perfect absorber and as well as radiator, so it will radiate all the heat energy in the form of all electromagnetic spectrum. So I mean to say, if we are giving a certain amount of heat energy to this black body, then it will radiate all of that in the form of all the lights, starting from gamma rays to the radio waves, and as well as the visible light as well. So I mean to say, and according to the Stephen Boltzmann law, it will radiate in the form of the different wavelengths, and those wavelengths will be like I'm showing you. I'm just trying to tell you that these lights will be all lights starting from gamma to radio. So according to Stephen Boltzmann law, all of these lights are radiated with different intensities, but one light among all of these lights, either it's visible or invisible, one light carries the maximum energy, maximum intensity. Okay, so let me show you in this graph that according to Stephen Boltzmann law, this is how all the lights are radiated from the heated object, in which kindly notice that this is of certain wavelength. All right, this is a lambda p, the peak wavelength. This light will carry the maximum intensity. And one more thing, remember that this is our visible spectrum. Okay, students, so generally this is our visible spectrum. So it can be a yellow light if the temperature of that object is 5000 Kelvin. Okay, students, so it means that if I will drop the temperature of that object, now that object will radiate, of course, the small amount of energy. But look at this point that now the peak wavelength, I'm talking about exactly this peak wavelength, is now larger because the temperature is 4000 Kelvin. Then this peak wavelength is a peak wavelength of green light. So just I mean to say, as you are dropping the temperature, wavelength is increasing. So it means that for more smaller temperature, for more smaller temperature, this will be the curve, and then it will going on. Okay, so if as we increase the temperature, it radiate more energy, and when it radiate more energy, so basically it radiate the light which carries the maximum energy. The wavelength gets smaller and smaller as the temperature increases, and according to Wien's law, we know that the product of the peak wavelength and temperature is constant. And I have shown you with the help of the Stephen Boltzmann graph as well that the lambda p is inversely proportional to temperature. Okay, so we have seen both mathematically as well as conceptually that its graph cannot be b, it cannot be d, because this is a graph basically of between intensity and the wavelength, so it cannot be d, it cannot be c, so a is the only right answer. So I hope you understand this solution.